Okay, so although this is lecture 15, but I wanted to start from the remaining lecture contents of lecture 14. So maybe you remember that our lecture 14 was particularly short due to my personal schedule. So I wanted to keep the discussion of lecture 14. So maybe you remember this one, the convention for electrostatic potential. So the convention is quite simple. So simply by this quantity, so the energy level corresponding to the electrostatic potential, we wanted to point out the intrinsic energy level of the reference material. In many cases, in our cases, so reference material equal to the silicon. So now think about this case. If we have, for example, silicon and metal, then consider the equilibrium case. In this equilibrium case, we can define the Fermi level and the Fermi level, and we may have vacuum level, the level where our electrons is no longer confined in this metal system. So there is the energy difference defined as work function, and work function is continuous across the metal silicon interface because this is vacuum level. So now we have a vacuum level, and also we can define the distance between its vacuum level and conduction band minimum, and also can define difference between conduction band minimum and its intrinsic Fermi level. So quite simply, we can define this EI as this way. EI of our reference material silicon can start from the Fermi level and work function, and also minus vacuum level minus EC, and also minus EC minus EI. That is our simple expression. Okay. So now everybody understand Fermi level can be defined as a zero electron volt. In this case, we can keep this out, and also from this convention, intrinsic Fermi level of our reference material is pointed out by our electrostatic potential. So now we can say that this quantity is corresponding to this way. So now we have the relation like this. So simply speaking, even when we have the equilibrium case, our phi electrostatic potential is no longer 0 volt, but it has non-zero value. So please note that when we apply our Poisson equation to this interface, metal semiconductor interface, we must apply this condition to consider this boundary value. Okay, so this is the one. And up to now, we have thought about metal and silicon interface. However, in reality, when we consider MOS system, instead of this silicon, we have silicon here and oxide in between. But our concern is the boundary value at this point. What is electrostatic potential of this point, not this point? However, still in this case, we can apply the same expression to this metal oxide interface because, please note that the electrostatic potential points out the intrinsic Fermi level of the reference material, not the material at that point. For example, when we have certain oxide node here, then it is easy to say that, okay, this electrostatic potential is trying to point out the intrinsic Fermi level of oxide, but unfortunately it's not. And even in this oxide layer, our electrostatic potential phi try to point out the intrinsic level of the reference material silicon. So that makes quite much advantages when we really implement this TCAD tool. So please note that even when we consider oxide or nitride or, for example, silicon germanium or germanium, we can consider many different materials in this silicon-based device, but for all other materials, we just define our electrostatic potential as the quantity corresponding to the intrinsic Fermi level of the reference material, in many cases just silicon. So please note this one. So now we are currently talking about the nonlinear Poisson equation. Nonlinear Poisson equation, and why we call it as nonlinear Poisson equation is because electron density and hole density, they are expressed as nonlinear functions of what? Nonlinear functions of the electrostatic potential. So, for example, if you remember correctly, then this is the form we have adopted, and this is the form we have adopted. Of course, please note that these kind of expressions are not perfectly well matched with our Fermi statistics. So instead it is based on Boltzmann statistics, but it is still okay in the approximate sense. So we will use this kind of thing. So if we really wanted to talk about the Fermi Dirac statistics instead of this kind of exponential dependence, what should you do? We must do the Fermi integral, which has order of half. So if you don't remember, if you don't understand this one, it's okay. It is just okay. Please note that this expression is just an approximated form for specialized assumption. Okay, so now if you remember correctly, then this system is like this. Here we have 5 nanometer thick silicon substrate, and here we have just half nanometer thick oxide layer and also half nanometer thick oxide layer. And now we apply the 0 volt to the gate and gate. Even in this case, as I told you before, in our example, we have this non-zero value for our boundary value. So although this is written as electron density, if we just draw phi, then at these 2 points we will have the values corresponding to approximately 3 volt. Okay, so now here we have oxide layer and here we have oxide layer. Since they are all oxide layers, so inside them we have no electron. That's the reason why we have no electron here and there. And instead, in this part, we have silicon layer, and in silicon layer we have electron density, non-zero electron density. Okay, so by solving your nonlinear Poisson equation, you can get this result that will be assigned as your homework problem. Okay, but please note that when you have this 0 volt case, when you apply 0 gate bias to this device, what is the value of your electron density? So can you read it? So what is the range of it? It is per cubic centimeter. This is a typical unit we have to keep in mind, and its value is just 10 to the 15. 10 to the 15 per cubic centimeter. So it means that there is nothing. Almost no electron is existing in this channel region. Then what is the meaningful value? So the inversion is defined as when we have more and more electron and the number of electron is corresponding to the doping density. So doping density is typically like 10 to the 17, that is small, 10 to the 18, that is moderate, or yes, and 19, this is high but not that high, 10 to the 20, that is high. So you have to have certain feelings about those numbers. Below this 10 to the 17, so you can just treat it as null number. So simply speaking, 10 to the 15 in this case, almost we have almost no electron inside it. That's the reason why when we try to use this system as a carrier conducting material, that is very poor. So if you ask me whether this layer can conduct current or not, then certainly I will say that no, it is not very effective to use this layer, the current layer, as a current conducting layer. However, if we introduce higher gate voltage instead of 0.0 volt, if we introduce 0.1 volt, 0.2 volt, then this number, the number of electrons inside this silicon layer, will be increased. And if we have sufficiently large number, high number of our electrons at a certain gate voltage, then we can use those electrons to conduct current. Okay, so please try to calculate this one. This is the case for gate voltage equal to 0 volt. And now we move to the concept of bias damping. So up to now, we have thought about the case where gate voltage is 0 volt. So, in this case, now I assume that you can calculate this solution easily. So actually, when you really try, you will find that implementation of this simple problem, seemingly simple problem, is not that easy, but I assume that you have achieved that goal. Then instead of having 0.0 volt, we wanted to move to 0.1 volt. Yes, in this case, how can we do the solution of, or how can we get the solution at 0.1 volt. Here we have a simple flow chart. Start at the initial bias. In our case, what is the initial bias? It is gate voltage equal to 0.0 volt. Then please try to solve the given bias. Yes, we get the solution at 0.0 bias. Then increase the bias. For example, 0.05 volt. Then try to solve the system. Then now you will get the solution for 0.05. After that, just increase the bias to 0.1 volt and try. Let's say that your final goal, for example, is 0.7 volt. However, you always start from, for example, 0.0 volt, and what you do is just to incrementally increase this gate voltage to eventually arrive at your target voltage of 0.7 volt. So are you all with me? I mean that if you are ambitious, then another approach would be just to jump into 0.7 volt, or even more, just to directly start from 0.7 volt. But unfortunately, in many cases, these kind of approaches, like starting from directly some highly turned on inverted channel, or just to increase your bias quite significantly, in many cases it does not converge. You fail to get the solution. That's the reason why here we have very slow approaches like this. So slightly increasing, and if we success, and slightly increasing once again. So this kind of approach is typically called as bias lamping. So we do not rapidly increase the bias, but instead of that, we slightly, moderately increase the bias to arrive at our desirable target value. So are you with me? So it is quite much a conservative way to get the solution. It is because if you fail during this bias lamping stage, then eventually you will get nothing. So let's say that your solution is, for example, you are much interested with your solution at 0.7 volt, but let's say that your simulation is terminated due to the poor convergence behavior. For example, your gate voltage is just 0.4 volt. Now assume this situation, that what you get is just nothing, because the solution at 0.4 volt is not the solution at your target voltage. You are interested with this bias condition. So intermediate solution appearing in this bias lamping, actually that is not that much interesting to all of us. So in many cases, in most cases, so convergence failure means the failure of your entire simulation flow. That's the reason why we are quite much afraid of convergence failure. So in order to reduce chance of convergence failure, we introduce small change in our gate bias and small change in our gate bias. So are you all with me? So that is our approach. So please note that we must do bias lapping. So in this case, what should be the boundary values at these two nodes? Like here we have MOS system once again. Here we have metal. This is a boundary, and this is a contact boundary, and OSO. So previously at gate voltage is 0, then we have applied approximately 0.33 volt to here when gate voltage equal to 0 volt. Then how about the case when we have voltage, for example, happen to be 0.7 volt? Then what should be the correct boundary condition for this node? The answer would be simply adding this number. Since gate voltage is 0.7 volt, our potential is also increased by the amount of applied gate voltage. So although that is not that much probable, let's think about simple example. Now we have two gate contacts. So for this one, I have applied 0.5 and I have applied 0.1 volt to this right contact. Then what should be the value for your electrostatic potential? In this case, it should be about this value for our example, and for this node we must have about this value for our left contact, because applied gate voltage is just added to the equilibrium value or zero voltage value. This is the value when we apply at when you apply the zero gate voltage, and we must add individually the applied gate voltage. Okay. So now when you have a look at its solution, then now you can draw this graph. This graph is quite important. So starting from gate voltage equal to 0, then we just increase gate bias slightly. Although our interest is mainly laid on this bias condition, but instead of just directly jumping to this 1.0 volt, we just make a journey to our target gate voltage. So we increase gate voltage, gate voltage, gate voltage, and get the solution. Once we get the solution, here you can see that this is electron sheet density. So electron density has the unit of per cubic centimeter. So this is the unit of your electron density. However, what is this sheet density or aerial density? This is the electron density integrated over your silicon layer. For example, this quantity is exactly given by this way, and starting from 0.5 nanometer up to 5.5 nanometer. It means that inside your silicon layer, you just integrate your electron density. Then please note that this electron has the unit of per cubic centimeter, and you know this integration over x, the real space position, introduce another dimension like centimeter. So that's the reason why the result of this integration will give us per square centimeter quantity, so area wise quantity. Per area, how many electrons are there? That is the quantity we have to keep in mind. And you know that its value is not like 10 to the 15 or 16, 17, 19, 20. So because we have a very thin layer, for example, 5 nanometer thick, and let's say that we have just 10 to the 15 per cubic centimeter in its average, then what will be the sheet density? If we have this kind of a constant integration, then we will have 10 to the 15 times 5 times 10 to the minus 7 centimeter. Please note that 1 nanometer is corresponding to 10 to the minus 7 centimeter. So we will get 5 times just 10 to the 8 per square centimeter. So this is quite low. That's the reason why we have almost zero value in the scale of 10 to the 13 per square centimeter. So however, now you can easily understand after some voltage later, for example, if you apply 0.3 volt, then you get now noticeable values, which is around corresponding to 0 point something times 10 to the 13 per square centimeter. Already it is order of 10 to the 12. So you know that here previously you had 10 to the 8, but now you have 0.7 volt, 0.3 volt, you have much larger values. How large is it? It is already about order of 10 to the 4 or 10 to the 5. Only by applying 0.3 volt additionally, you can change the number of electrons collected in your double gate system by factor or by orders of 4 orders or 5 orders of magnitude. Okay, that is beauty of this MOS system. Using very small change in your applied gate voltage, you can easily modulate the number of electrons you have in your system. Okay, so I already cause this is 0.3 volt. So how that can happen? So 0.3 volt, that is corresponding to 300 millivolt, and you can easily understand this is 5 times of 60 millivolt. So as a rule of thumb, in these days, in order to increase your electron density, your sheet density by factor of 10, you need 60 millivolt. So it means that 0.3 volt is sufficient to increase your electron density by 5 orders of magnitude. So that is quite much corresponding to your previous assumption. So yes, it was orders of 10 to the 8, and it is now orders of 10 to the 12 over 13. So there is certain differences like 10 to the 5 or 10 to the 4. So yes, within this 300 millivolt, you can achieve this drastic change. So this is your homework problem. So please reproduce this result or these graphs by yourself. Okay? So once again, I want to say that how can you prepare this electron sheet density? As a solution of your nonlinear Poisson equation, you will get the electron density everywhere inside your system. Then please integrate it over the silicon layer only, because oxide layer doesn't have any kind of electron density. Then this value will be your y-axis variable, so shown here. Okay. Do you have any question on this homework problem? No? Okay. So, okay. Then that was the lecture content I have prepared for lecture 14. So now let's move to lecture 15. Today's lecture, we will still keep discussing about the Poisson equation. Okay. So continuing our discussion once again, now consider another example. Our previous example was double gate MOS system. So 5 nanometer thick MOS system, double gate. But now we are now considering abrupt PN junction. So now consider, for example, 400 nanometer long structure starting from 0. It ends at 400 nanometer, and we assume that metallurgical junction is located at the midpoint, so 200 nanometer. And here we have N-type layer, and here we have P-type layer. Okay, so now we apply the constant doping density at N-type layer and also constant doping density at P-type layer. But we assume that N-type doping is higher than P-type doping. That is the situation typically seen our NMOS device. Okay, so of course, if we go to PMOS device, we have a completely the opposite case. We say that in this case, P-type doping density is much higher than our N-type doping density. But for a while, just to consider this kind of N plus P doping system. Okay. In this example, do we have oxide layer? No. Here we have only purely silicon layer all over our system. So our previous discussion on the boundary values, boundary condition, does not apply to this case. Then here still we have two boundaries. Here we have one boundary and another boundary. How can we set the electrostatic potential at 0 nanometer? And how can we set the electrostatic potential at 400 nanometer? So if you remember our previous discussion, in order to calculate this value, previously we had to consider this kind of description. So work function of something, our metal, and we must consider this kind of thing. However, in this case, this is not available. So instead of that, we must find another boundary condition for ohmic contact. So please note that the boundary condition we have considered up to now was for our metal oxide interface. Okay. Now instead of that, now we wanted to consider metal semiconductor interface, the contact. in this case, we just calculate the electrostatic potential from our doping density. We have already seen it before, and please use this value for our contact value. This is nothing but our phi equal to phi 0. So this is identical. So we are now saying that our electrostatic potential is given by just doping density. Yes, if doping density is given, then our electrostatic potential is given. Maybe you feel something weird when we consider previous boundary condition. Our previous boundary condition was like this. We had the values of applied bias voltage. But I'm now just saying that phi equal to phi null. Why I'm doing this kind of job? Okay, if we have a certain applied voltage, then it's true that we can just add this one. But this one will be reserved for our next discussion. For a while, just to consider the case where our applied voltage is exactly 0 volt. So since it is 0 volt, so now we can say that we just apply the electrostatic potential equal to the equilibrium potential. So now let's go to our example. This is N plus P junction. Why we have positive here? It is because relatively the N-type dopant is more than P-type dopant. And of course, in order to say something to N plus, there is some feelings about this number. For example, if we have 10 to the 15, we never say that is corresponding to N plus. So usually when we say N plus, at least it should be orders of 19. But that is not that high number, not that much high. So if we have 20, then it is sufficient to call it as N plus. And sometimes we can have the values like 5 times 10 to the 12. Then in this case, sometimes we add additional plus sign to represent that, oh, this is really high doping density. But anyway, when you say that N plus P junction, then N plus is corresponding to like 10 to the 18, 19, 20, and P is lower than that. That is the case. In this example, I just select one typical values like 10 to the 20 per cubic centimeter as a N-type doping density. So in every case, it is absolutely much higher than our P-type doping density. Then now we have changed the P-type doping density. For example, 10 to the 17, 10 to the 18, and 10 to the 19. Oh, 10 to the 19 is already quite high. However, in this scene, everything is really relative. Since N plus is 10 to the 20, and since P type is 10 to the 19, so this is still can be called as N plus P junction. And here we have every interesting thing happens only in this p-type result. So please have a look at the behavior of your electrostatic potential. So this is the metallurgical junction and this is the metallurgical junction. My question is where the change of interesting physical quantity happens, in this n-type region or in this p-type region, where the potential changes. potential changes only in this p-type region. In n-type region, nothing happens. Please have a look at this part. This is 10 to the 18 case. Still, everything just happens in this p-type region. Even this 10 to the 19 case, although the width of this change is much narrower than previous case, however, it is still true that only changes occurs in the p-type region. That's the reason why we are much interested with which one is dominant. In this N plus P junction, where N-type dopant is much more than P-type acceptors, then everything, the change of physical quantities occurs in this p-type region only. So now we can say that this is the case. Then of course you can draw the same quantity by your own program. Then please try to reproduce this kind of things. Yes, you can do it. So now we have homework 13. However, from this homework 13, now I will enlarge the due period. So previously we had just 2 days or 5 days, but from this one you have 1 week to solve this kind of homework problem. Homework problem 1 is please reproduce the graph shown in our previous lecture. What is it? So let me just go to this one. The homework problem 1 is, once again, this one. This one is the graph you must reproduce to do homework problem number 1. So in order to achieve this goal, you must do 2 things. One thing is to achieve this solution at 0.0 volt. After that, you must implement another loop to increase your gate voltage. So that is done by, once again, this procedure. First, please implement the solver at a given bias. So, for example, 0.0 volt, you can solve the system. After that, once you get this code, then now you can introduce the increments of your bias voltage. When you achieve these 2 goals, then now you can get this kind of graph. Of course, in order to get this y-axis variable, once again, you must integrate your electron density. That is your homework problem 1. And homework problem 2 is, please just reproduce these graphs. Okay, so you can do it. I have to say plural forms like please try to reproduce the graphs shown in our previous slide. Yes, you can do it. However, actually this problem 2 is much more easier than problem number 1. The reason why I have introduced this problem 2 is like this. If you just directly try to solve this problem 1, maybe it would be very difficult to most of you. So instead of directly trying problem number 1, please start from problem number 2. It doesn't have any oxide, no oxide, only silicon, and boundary condition is quite much easier than problem number 1, and there is no bias lamping. You can just solve the system where applied bias equal to just 0 volt. So problem 2 is an easier, relatively easier problem. And once you get the solution for problem 2, then move to problem 1. Okay, so are you all with me? Then let me just cover the remaining steps in this lecture 15. Okay, so now it's time to announce our term project. Okay, so most important thing is the theme is your own choice. So I think that you have a different background. Some of you came from ECS, some of you came from physics department, and some from material science. So you have different background and different research interest. So please try to set your own theme. Okay, then please share it with me. Then I can give you the possibility of your term project. And as I announced many times, your term project will be posted in my YouTube channel. So please prepare your term project at your best effort. And due date is December 18th and early in the morning. Please send a recorded video to me. Then based upon the quality of your recorded video, I will give you your grade. So why don't we just show the calendar? So unfortunately I cannot show the calendar in this screen, but this date was selected because this is just next Monday after our final examination week. So we have a week reserved for final examination. So I think that will be too busy to ask you submit your recorded video in this week. So instead of that, after your final exam is over, then the next Monday is set as your due date. Your due date is not extended at all. So just although that is not perfectly prepared, please keep the due date. So no late submission will be accepted, and if you fail to submit a recorded video, then that will significantly degrade your final grade. Okay, so please keep the due date. And I have just prepared the list of our previous term project. So 1 year ago, so 3 students submitted their term project. So you may find that they are all recorded in Korean because they are Korean students. 2 Korean students, you may use the Korean, and of course for foreigners, then you may speak English. Okay, either one is quite much acceptable. So please watch the previous term project, but they are all, I think that in many cases your interests may not be fitted with this previous term project. I really encourage you to do the term project which is related with your own research interest. So for example, if you are coming from circuit design lab, then maybe you can try to do some circuit related jobs, then I can assist you. And if you are coming from, for example, material science, then maybe you are more related with the properties of a material instead of this transport one. Also, you may have different materials. Although we are now talking about PN junction or just MOS system, which are far most important in our application, but if you have a different device of your interest, then you can use those kind of devices for the basis of your term project. Then maybe that can really helpful to your own research work. That is my recommendation. Okay, so now this is the last homework problem. Please write down your plan for the final term project, and I will read your plan and will give you my feedback on your term project. Okay, and maybe you have about 1.5 months. Approximately you have 1.5 months. So this is to somebody that is quite long enough time, and to somebody that is too short to prepare the term project. But anyway, please start now. It is now time to start this one. Okay, although we have still more than 20 minutes left, but just I just wanted to stop here and to listen your question or get your question about this term project and your homework programs. If you have any question, then please feel free to ask me your questions.
텀 프로젝트 일단 주제에 관해서 어떤 문제를 선정하고 푼 다음에 그 발표하는 영상을 제출하는 거예요? 아니면 그 레코드 비디오를 제출하는 게 무슨 뜻이에요?
Okay, so let me just restate his question. He asked me about a more specific form of this recorded video. That is like this. For example, if you let's assume one case. Some of our previous students just select the simulation of a NAND device as his theme of a term project. Then in his presentation, he just introduced what is NAND and specify which NAND is simulated and equations to be implemented to simulate NAND, and show some simulation result. After that, make the conclusion. So this kind of PowerPoint presentation was recorded, and that recorded video was sent to me. So you may find these three well prepared term project. So please watch, and you may get some feelings about what is actual term project of this course. This is a really good question. And any other question from our students? Okay, I wanted to say that although we are now talking about process simulation and device simulation, however, you are free to select your own research topic. I mean that although you have not thought about, although the approach was not covered in our lecture, the regular lecture, it is completely okay. I just wanted to encourage you to find out your own system and your own approach suitable for your program. Okay, so don't be confined on our lecture content. So this is just for specific system like more or less MOS system, because this is most important in real application. However, you may have different application. Then I just obey or respect your own research interest. Then please. For example, one example is circuit simulation. Circuit simulation is never covered in this course. However, if you are interested, you can start the circuit simulation. That is one thing. For example, density functional theory. Density functional theory is never covered in this course. However, if you are interested, then you can try to build up your DFT code. Then I can help you to how can you do this kind of thing. You can find many other ones. So that's the reason why problem number 3 is show your plan. Is it because if your plan is beyond my capability, then I would say that okay, that sounds good, sounds great. However, this is beyond my capability, so I cannot give you my help. So you must choose go without my help or just try to find out another topic for your final term project. The reason of taking this homework problem 3 is just discussing about your final term project. Okay, so are you all with me about the purpose of this problem number 3? So please think, and your due is not this Wednesday, but you have 1 week to all think about problem number 3. Please be careful and be serious about making your plan. Okay. Any other question from our students? Okay. Okay, if you don't have any questions, then today's lecture is over. Thank you for your attention.